Okay, so here's the last session. Really excited to kick off session 3 with TJ from Google telling us about some of the exciting challenges accelerating HPC applications on TPUs. Please, TJ, take it away.
Thanks, Jack. Hey, my name is TJ. I'm an engineer at Google Research. So I'm going to talk about accelerating scientific computing applications with TPUs. So the recent success of deep learning spurred a new wave of hardware accelerators. One such example is Google's TPU, Tensor Processing Unit. So TPU has the strengths in tensor operations. It's always tempting to ask, other than machine learning or deep learning, whether TPU can be useful for scientific computing applications. And we seek an answer to this question through the following case studies. So before we dive into the case studies, I would like to have an overview on the architecture, TPU architecture. So this is a TPU v3 hardware architecture on the right, from chip package level, board level, all the way to system level. So TPU is designed as a coprocessor on the I/O bus. It's a similar concept applied to a GPU. For a TPU v3 board, it has 4 chips. So 4 chips on the board, and 2 cores for every single chip. So one TPU board pairs up with one CPU host in a pod setting, the pod setting. So if the system level is actual pod, for pod setting, there is a total number of 48 cores. And so in TPU, there's this unit called MXU, matrix multiplication unit. The MXU provides the bulk of the computing power. For TPU v3, every single clock cycle, there is 16K multiply accumulated operations. And those TPU cores or chips are connected as a 2D torus. So the interconnect topology is a 2D torus based. So that interconnect of the 2D torus network is dedicated and on device, which means it doesn't go through any host CPU. And TPU use high bandwidth memory. So later on, when we try to solve these scientific computing applications, so we need to design the building blocks based on the TPU hardware architecture. And that's how we do it in the following cases. So for the case studies, we have a Fourier transform, a DFT, FFT, and a uniform FFT. And we also have a linear solver, which is the conjugate gradient method. We also dive a little bit into the numerical optimization from the alternating direction method of multipliers. And I will combine all these building blocks into the medical imaging reconstruction. Here we go. This is the Fourier transform. So Fourier transform is critical in many scientific and engineering applications. The general form of DFT has a matrix form. So we can write a DFT in terms of matrix factor multiplications as Vx. So V is the trivial factor matrix, X is the input. So that makes things a little easier on TPUs. So in order to compute this matrix factor multiplications Vx on a bunch of TPU cores, we need to come up with a parallel algorithm. And we propose the one shuffle scheme. You can see the figure B. So that's a 3D input, which means we're going to do a 3D DFT. So first, we partition the 3D giant tensor, into smaller 3D blocks. And we distributed the smaller 3D blocks onto individual TPU cores, so that we can sort of localize the tensor operations on individual cores. But we do need communications. The communication is through collective permute, which means, for example, on figure B, core 1 will contain a block of data. And then, so in each iteration of the collective communication, core 1 will send its data to core 0. And at the same time, core 1 will receive the data from core 2. So in this case, the communication takes place simultaneously along the same direction of the interconnect network. So this way, we can achieve very high parallel efficiency. Let's see the scaling analysis. So this is 3D DFT of size 2K by 2K by 2K. We plot a strong scaling from 32 cores all the way to 256 cores. You can see that this scaling denoted the actual scaling in terms of computation time is approximately linearly or close to linearly. So DFT is expensive algorithm, but there's a better way to do Fourier transform, which is FFT. For endpoint transform, the computation complexity for FFT is n log n, whereas it's n squared for DFT. So that we have to, we also need to parallel the FFT algorithms. So before we do the parallelization, we rewrite this FFT as a phase adjustment term multiplied by a localized transform. In this way, we could utilize the one shuffle scheme, which means we can localize this transform operation on the individual core, while before doing the collective communication, we apply some phase adjustment. So that's the whole idea of this distributed FFT. If you want to dive into the scaling analysis, so we have a 3D FFT, and then it has a fixed problem size of 2K by 2K by 2K, the same as the one we used to show the scaling analysis in the DFT. And you can see that the runtime or the computation time scales close to linearly from 16 cores all the way to 128 cores. Actually, I truncated this scaling beyond 128 cores for the better visibility. The scaling is close to linear all the way to full pod. But FFT is not enough. We still need a better algorithm for handling Fourier transform in the medical imaging domain, because most of the data are non-uniformly sampled or acquired. So we need a NUFT. NUFT is operator short for non-uniform fast Fourier transform. It consists of 3 operations: optimization, and FFT on a regular or uniform grid, and interpolation. Among the 3, interpolation is the bottleneck. So we also utilize the one shuffle scheme, and then so in this for the NUFT, we have compared the runtime of FFT on TPUs with the runtimes on the other 2 types of hardware platforms, CPU and GPU. So this table shows the NUFT on various sizes of image, and for both for CPU, GPU, and TPU. You can see that a TPU achieves comparable runtime to GPU, and both GPU and TPU accelerate this NUFT operation, and the runtime is significantly faster than the one on CPU. So next, we'll combine these operations in a medical imaging reconstruction problem. The reason of doing medical imaging reconstruction is for 2 reasons. We have 2 reasons. So one is MRI, magnetic resonance imaging, is a powerful medical imaging modality, and the second is the computation is the bottleneck. So this because of the data acquisition speed is approaching the physical limit. If we want to further accelerate the MRI, it requires breaking the Nyquist sampling frequency. And the state-of-art MR image reconstruction often build upon large-scale iterative optimization methods. So we want to give TPU a try on this computationally challenging problem. So this figure shows this first equation is the MRI measurement. So D is the measurement, and beta is the computation. Is the image complexities. It's complex numbers. So in compressed sensing, one can reconstruct an image from the undersampled k-space data by solving a optimization problem. This problem has 2 terms: data fidelity term and sparsity constraint terms. So we use ADMM to solve this problem, and ADMM has 3 updates. For update of mu and eta, this auxiliary variable and then dual variable, we have a closed form terms. For updating the computation, this complex imaging intensity, we have to solve a regularized least square problem. That's how the CG solver comes into play. So this is the algorithm we do to solve this problem. The update of auxiliary and dual variable are local, and the update of the primary variable is through the CG solver, where it requires the communications. So we're actually using the cross-replica sum to sum the partial image across all the TPU cores, so that in the new CG iteration, it starts with the same image. So this is the benchmark on accuracy. So we have phantom data, and this k-space data were retrospectively undersampled with an undersampling factor of 8. And the total number of k-space data is close to 20,000. So we reconstruct the image of size 128 by 64. And the relative difference is about 1% for the voxels within the phantom. So this figure shows the phantom, A, B, and A is the phantom data we used, and the B is the, so A is actually the single inverse of DFT without the iterative scheme. So B is the reconstructed image on CPU, and the C is the reconstructed image with the TPU. And we also draw two center lines of accuracy. So we do a horizontal center line and vertical center line, and we plot them in this figure. You can see that within the voxel range, the phantom range accuracy is close to 1%, which is considered as the satisfactory accuracy. So the next is the performance. So we do a parallel efficiency analysis. It's the same as the DFT, FFT. We're using the strong scaling analysis to understand how much efficiency we can get on TPUs. So again, we take a larger set of phantom data. This is acquired by using 804 radio results, each with 1K samples. So the total number of the case-based data is close to 1.2 million, and we do the reconstruction problem on CPU, GPU, and TPU. It can be seen from the table that for TPU, image 128 by 64, we have a significant speed up. Whereas for larger examples, the speed up is less significant, but we do see a speed up over CPU and the performance comparable to a GPU. The reason is so we're using DFT in this problem. The computation complexity is higher than a NUFT, and we are working to incorporate this TPU NUFT into this reconstruction pipeline. And the figure on the right are the scaling analysis. So I think all from 2 cores, 4 cores, all the way to 8 cores is closer to linear, and beyond this 16 cores, the scaling, the speed up saturates because the problem size is kind of small for this hardware setup of 16 cores. That kind of concludes my talk. So through this few case studies, we are exploring using TPU for scientific computing applications. The applications consist of Fourier transforms, linear solver, ADMM, and their applications in medical imaging. So we formulated the problem and designed an algorithm in accordance with TPU's strengths in test operations. And we do see TPU achieves good accelerations for these applications. That's all I have today. Thank you.
Nice. So there's a couple of questions here in the chat. Santosh was asking, what data type is this? Is this all bfloat 16? Is it integer? What does that look like?
It's a single precision. TPU MXU takes floating 32 and output floating 32, but the operations inside MXU is bfloating 16. But we do have a accumulation decomposition way to achieve an accuracy similar to floating 32. So that's a single precision for the entire work.
And then Ganesh was also asking, are these codes going to be available anywhere as benchmarks?
Yes, we are also, I think for DFT and FFT, we are open sourcing this code under Google Research. Since we're still incorporating the new algorithm into the ADMM pipeline, we have a target to open sourcing this code. But we also have to talk to our collaborators on this kind of code releasing thing. Yes. So, yeah, open sourcing is the goal. Yes.
Yeah, thanks. And these are Google TPUs, right? Not NVIDIA's Tensor cores.
No, this is on Google TPUs.
Okay, thanks.
So maybe one question along those lines. You mentioned sort of considering the communication patterns for how to best target the TPU. Is there any kind of, you're really smart. You have a team of really smart people who understand the architecture and understand the algorithm and understand the numerics and can figure that out. Is there any sort of systematic approach for how to adapt to these architectures and their different numerics and different communication patterns, or is it sort of still a case-by-case basis?
That's a very good question, Zach. So so there are existing parallel algorithms in XML compiler, for example, G-Shard or GSPMD. So those algorithms are built in the compiler side. So which means we can do data annotations, and the compiler will handle this distribution automatically. So that's one way. This way is because TPU or TensorFlow or JAX those are devised for machine learning applications. So we usually will have a model dimension and a data dimension. So those sharding or distribution mechanism are orchestrated to fully take advantage of the machine learning applications or workload. So on the other side, so those you can easily use TPU or TensorFlow or JAX existing like PGIT or SPMD to achieve it. On the other line, so for scientific computing applications, so those workload are different from the machine learning workload. So we need to have a finer control on the collective operations, have a finer control or stronger control on the data sharding or data decompositions. So those kind of things we have to orchestrate this parallel algorithm ourselves. So there are two lines of it, but I mean it really depends on the workload we're dealing with.
Absolutely, yeah. I think this is going to be a really exciting area to keep pushing on, but it's interesting to also think about decomposing it along sort of the ML lines, because that's how the hardware was built. Super excited for this stuff. I think in the interest of keeping on track, we're going to go ahead and switch over to Mike. But thanks very much, TJ. And again, if folks have questions, please pipe up in the Slack or the chat, and we will make sure to get things routed.
Yeah, great to see Google people. Thank you so much for coming.
Thank you.
All right,